afternoon, everyone. Welcome to Warringah Mall Library for our local author programme. I wish to acknowledge the traditional custodians of these lands on which we gather and show respect to the elders past and present and other Aboriginal people here today. If you could please take a little moment to turn your phones to silent, that would be really great. And today we welcome to our library local author, John Ball, as he discusses his recent release, How to Solve AI with Our Brain, the Final Frontier of Science. Please welcome John Ball.
Thank you. So it's a book tour, and so I might as well talk about what the book is, and a little bit about where it came from. So that's the title, How to Solve AI with Our Brain. But when I was pretty young, 6 years old, I used to watch this thing on TV called Star Trek. And most people like Captain Kirk because, you know, he saved the universe, the galaxy. But I was really keen on this other guy who wore a red shirt, and he was the only one that wasn't killed in the particular episodes. It was Scotty. And Scotty had this knack of, you know, crawling into a tube, he'd tighten a screw, and then the Enterprise would be saved. And so when I was 6 years old, I decided that's what I wanted to be. So a few years later, my father was an academic in the US, and he was the one that did the psychology work for Sesame Street. And he took me to where he worked, ETS, they do the SAT tests in the US, and I got to work on a mainframe computer when I was 9 years old. So 1972, I was using basically what became the internet, and it had all these educational tools, and I thought, I'm on the path to Scotty. And so fast forward about 20 years, and I'm working for IBM, and I'm a mainframe engineer, and I had my Scotty moment. So I achieved my Scotty moment at about 29. We had a mainframe in North Ryde that had gone down, and the machine had come back up, and they had this software problem. There's like kind of 50 people standing around. What do we do? They tried something, it didn't work, and I just said, do a cold start. I did the cold start, it all worked, and that was it. I was the hero for 15 minutes, and my life was finally achieved at that age. Unfortunately, I also then had this experience at City University, and my teacher said just before I graduated there that we're never going to understand how the brain works. And I've never really done much work in my life up to that point, and that was just enough motivation for me to go to the library for the entire summer, read every book I could on cognitive science, which is psychology, linguistics, computer science, philosophy. I read all those books, and I just kept working on, I've got to solve this problem and prove her wrong. And since then I've gone back and I've explained to her that, you know, here's my theory, and thanks for costing me 20 years of my life to prove you wrong. and you can read about that in the book. The other thing that happened was I was working with Marvin Minsky, the guy that was the top guy at MIT in AI. He was involved in the original definition of artificial intelligence in 1956. And when I contacted him, he said, sounds like a good idea, but you've got to prove that it works. So half of your job is to explain how your theory works, and the other half is to prove that it works. So in 2006, so 20 years ago now, I then made the decision, I've got to leave my day job and prove that I can make this system work. And I'll be showing you the system as we go through that proves that we can use this technology for good and to improve on the AI that is available today elsewhere.
John, do you want to mention about the recording?
Oh, yes. So I've got two cameras here. So I was probably going to put this up on YouTube in the next couple of days. If people don't want to be involved, just, it'll probably be the backs of your head anyway, but I am going to record it, and if anyone has a problem, just let me know. No?
Oh, it's just the back of my head. Liz was looking at my ball spot the other day. Cut that out, delete that, and I've got no problem.
Excellent. So I've got one there and one there, so you probably can't get your head at all. There's my book, How to Solve AI with Our Brain. That actually took about as long to write as most of the chapters to get that title right. So how to solve AI with our brain. I was just going to call it How Our Brain Works, and somebody pointed out, well, there's lots of books on that. What's the difference? And I realized that it's AI today is being done by computer scientists. And the theory is, as a computer scientist, you can model what people do and then build a model. So it's using machine learning these days. So these machines gather statistics and they do the things that they do, like ChatGPT. So it's great for what it does. It's not like a human brain. And what I wanted to do is then, with this book, draw the contrast between what the human brain does and what AI is doing in the mainstream world at the moment. And then I point out that it's the final frontier in science. And why is brain science the final frontier in science? Well, if you look here, here's a scientist. He's doing some sort of med work. He's got his telescope, microscope. Thank you. And there's all sorts of gear that makes this work really well. We know everything down to these very small levels. Over here we've got what looks like a spaceship going up. We seem to be pretty good at that sort of technology now. Yeah, come on in.
Sorry.
And then over here, that's a diagram of how the brain works. It's just the vision system, so we've got eyes that have a particular path that gets into these different regions. And what's interesting about brains is we know through brain damage what actually happens that's not good. So we've got down here faces. So if you have damage to this area on both sides of your brain, you can't recognize human faces. You sort of get a picture, you're seeing it, but you can't interpret it as this is somebody that I know. So there's people that have written books about the horrible situation where their spouse has this particular type of brain damage. They see them, they don't know who it is, and then they speak and they go, yeah, you're my wife or husband. And there's lots of different areas that make no sense. How is it that the brain can do this? Motion. You could lose the ability to recognize motion. So you're standing on a street corner and you look over to the right and there's a car and you see the car and then it vanishes. And then you see it again and then it vanishes. And that's the effect of losing that particular brain region. And the interesting question is, well, how does all of that come about? And is it important? And that's where cognitive science comes in, because if you can explain all of that, which this book explains, then we're a long way ahead of just thinking about how can we make this work, which is the computer science default position, just make it work. So I think we know everything in some detail, and the question is, how does the brain work? If you were to have a guess, and you were like 99.99% of the world, you would say it's like a computer. You can see a neuron, you've got stuff that goes into it, it does something, and then it signals and connects to a whole bunch of things. And so people call our brains the most complex machine in the universe. And it's pretty impressive. We're certainly better than the other animals on Earth because we have speech, and the ability to communicate with others with language is a remarkable feat. But it's not like a computer in a couple of key ways. And the distinction that I make is, back in the 60s, people were saying, back before that, people were saying, if here's my neuron and things are going in, what the neuron does is it sort of adds up the inputs, and there can be positive and negative inputs. And depending on the total, it then triggers, and then it releases connections to everything that it's connected to. And then those things do the same thing. And that's seen as a computational model, and if in computers, that's basically what a circuit does. You've got inputs, it does something with some sort of process, and then you get an output. Another way of looking at it is, if it fires, it's just match something. And so the idea of pattern matching is the different paradigm. So I'm going to go through basically talking about AI, and I'll talk about cognitive science and brains through this. So we're going to start off with how does language work? And in 2006, I started doing this work. I sat down at my desk and complete blank. I've got no idea what to do. And so after about 2 months of going to coffee shops and doing all sorts of images, I worked out, okay, this is the code I'm going to write. I'm going to write something that shows that we can interpret language with this pattern-based system. And
Attention please, this is centre management. The Chief Warden is investigating the alarm. I repeat, the Chief Warden is investigating
I didn't even know we had an alarm.
Please stand by for more information.
Oh, of course. Okay, so I'm working on this problem, and after about 4 years, I realised that I can do all the things that I need to do with pattern matching. System's working well. I've got one little problem, which is I don't know how English works. So I can match all these patterns. It's not doing what people have done before. And what's the solution? Well, I thought, well, I'm going to spend the next 30 years of my life working out how English works. And that was pretty disappointing. But anyway, I kept working on things. I went to Princeton, where I grew up. You can sort of tell by my weird accent that I'm not completely Australian. And in Princeton, my sister took me to a coffee shop. And in the coffee shop, I found this book. And the book actually explained how language works. Like all the things I wanted to do, but not only how language works, how all of the world's languages work with a single model. And I'll show you some diagrams just so you can get a feel for the complexity that this other guy's already done. And after a while, I chased him down. I chased the author down, chased the guy that wrote the theory, and we've been working together for about 10 years now. So here's this simple model. Syntactic representation, so words and phrases, which uses some sort of linking algorithm to meaning, and then all that takes place in this thing called discourse pragmatics. I worked with this guy and his theory for like 8 years, and I kept talking about context and whatever, and he's got this discourse pragmatics. I had no idea what it meant, but it sounded really good. And it turns out that's context as well. So, he always kept nodding. I'm thinking, why is he nodding? That's because I was using the right word, but he was just using a more precise one. So on this syntax side, we can actually look at how different languages work. Yeah. So in English, if you were to say the man gave the dealer the car, what we're seeing here is that the man is the one doing the giving, the dealer is the person who gets it, and the car is the thing being given. And in English, we put the words in a sequence like that, and we'd often say, well, there's a noun and a verb and whatever, an object, direct and indirect object, whatever. But other languages don't work like that. And here's one: the man, the woman, the book, it to her he gave. This is an individual word, and in that language, you put these words in that sequence, the man, the woman, the book, and then this verb gives you all of the information you need to interpret the sentence. You think, wow, that's kind of a crazy language, why would you do that? But then you can go to this language where they put the verb first, so it's C, and then you've got the man, the woman. And so when you look at lots and lots of languages, there's this pattern that comes out that says you can pretty much do whatever you like. The brain's good at doing this type of thing, and these guys have worked out, well, what would that look like? So that's the syntax side, so it's the words and the phrases that make up the language, and that connects to semantics or meaning. And so on the meaning side, if you give the dealer the car, it's the man that's doing something, we don't know what he's doing, which causes the dealer to have the car and the man not to have the car. So it's this exchange. And what I've been able to show is that by using this meaning representation, you can take language in, convert it to meaning, and then you can produce responses in whatever language you're interested in, because we're just working off the meaning, which is the same for all languages. And then there's this last bit of context, which is just remarkable how incredible language is for dealing with very complex things with like one or two words. So if somebody says Taylor married Ridge, okay, what if Taylor didn't marry Ridge? Well, you could say, no, it was Brooke who married Ridge. So that's an awful lot of words. And rather than use that big string of words, what you could say is, no, Brooke did. And those three words mean no, Brooke married Ridge. And when you look at long sentences, I realised that you can simply identify the correct short answer, and then we can get the machine to automatically produce the response.
Simplify it in computers, is that what you're saying?
We can do that on computers, yeah. And because linguistics isn't a solved science today, there's lots and lots of theories. The one that I follow, relevant reference grammar, seems to be the gold standard of how to interpret languages, because it has these three pieces. Lots of different linguistic theories just leave out the context and they leave out the meaning, and they're just trying to do it with patterns of syntax.
Can I ask who was
Yes.
the language theorist?
The theorist is Robert D. Van Balen Jr., so Robert Van Balen. He's a little bit older than me, but he's just retired from university work at Dusseldorf and Buffalo University in the US. Dusseldorf's the German university. Okay, so here's an example of where context is needed to have human-like interaction with AI. So this is the Microsoft Copilot, and I've written, "The Wizard of Oz is a good man, what can he do?" Now, the answer it's giving us there is, the Wizard of Oz, he turned out not to be a real wizard, just a man behind the curtain. Now, the Wizard of Oz could be my neighbour. That he could be a wizard, he could call himself the Wizard of Oz, and if I was a person and I said, "The Wizard of Oz is a good man," what would you say? Probably say, "Oh, you mean the book or the movie?" And then I'd say, "No, I mean my neighbour." "Oh, I don't know your neighbour." "Oh, okay." So you wouldn't immediately start giving me War and Peace about a particular book, about a cowardly lion and Dorothy and all this stuff. So that the key to the next generation of AI is to understand like a person does, and not just take for granted that this is the most probable answer, and now I'm just going to give you a page of stuff which is all wrong. We want to be able to interpret what the person wants, and then once we've validated it, then you can keep working. And there's a bit of science behind it. So here I'm saying the referent is that the Wizard of Oz is learned on the fly. That's how people work. And there's a bit of explanation here. So context is not one thing. So context is the interaction. So we walked into this room, I'm talking. I'm John Ball. You could probably recall in a couple of days that you went to this event, and I had a microphone that was probably a bit boomy. And what's happening is that we have a concept of immediate common ground. So while we're in a particular situation, we're tracking who's there, what's happening, where we are, where they are. And so this immediate common ground is where you can use pronouns. I can say she did this and he did that. I can point, and you can work out what I'm pointing at and then work out what's going on. So that's a key concept which is not in today's popular AI. And then there's this other concept of general common ground, which is I know about the world. So if we talk about the US, we could talk about Donald Trump, and we could talk about what's happening in the world with wars and things. That's general common ground. But once I introduce it into the conversation, I can say it's this and it's that. He's this. You know what I'm talking about. You know correctly what I'm saying. So we need to have AI with the same things that humans have in order to replicate humans, and that's the concept of using linguistics in AI. I thought I'd just have to show you that there is a bit of science behind it. You're not going to be tested on this. All sentences in the world fit into this model, and all reference phrases, so all noun phrases fit into this model. So an example here is Sally's two red parrots. That's a noun phrase, if you like. But you can also bundle a whole sentence into that, like the company's construction of the bridge in New York City, which is a very different concept to this one. And we've taken advantage of that with the system that I'll show you in a moment. Hey, I'm talking about a book. It's, you probably want to relax a little bit. So I've got this picture here that shows you what my patent looks like. It took 10 years to get approved. But what it shows is how you can recognize language. So basically, you take something like the cat ate the rat continuously, slowly on the mat today, evidently because it was hungry. We work out the syntactic pieces, and who knows whether it's right. We then use this linking algorithm to work out what does this actually mean. And there could be multiple interpretations of what we're seeing there. And so by then mapping it to its meaning, we can work out, does this meaning make sense? And ideally, does this meaning make sense in the context that we're using? And if all of those things make sense and we've only got one answer, now we've got a system that works, which has been the holy grail for language systems for 70 years.
John, if you create a system, how does it work if you want to use it in a different language? Does it know to read it? I mean, how does it work? Like, for instance, if you've done this in English and
Yep.
somebody wants the same system in French, how do they get it? Do you have to translate? What do you do? Or the system knows to read it?
Perfect question. We're coming up to that on the next slide, but this is meaning. So this is language independent.
Okay.
This bit here is determined by the words that you're using, because you use different words in different languages. If you use the same word in different languages, the phrases then help you work it out, and then the linking to the meaning representation disambiguates it fully. Perfect question. Thanks, Phil. So this is showing again, language-specific stuff. So the words and phrases come from a particular language. All of this stuff below is the language-independent stuff. This is part of the Roland reference grammar, linguistic theory. And the reason I don't cover much of this in the book, the book's much easier than what I'm talking about now. The Roland reference grammar book's like that thick. That's the latest one, and it's written by like 10 or 20 authors on very specific things. But the point is that when I'm talking to people who are AI experts in other areas, they're not aware of this information. They're not aware of the work that's been done over something like 40 years that we can take advantage of now. And here's an example of, if anybody speaks English here? Yeah, okay. Right. So when you think of the concept of seeing, it's not just one thing that doesn't apply to anything else. It's a word that's a state. So if let's see, the types of predicates. It's tough to talk in general terms without using the complex words. So there's things that are states that don't change, and there's things that are activities that people do. So in terms of seeing, if it was an activity, you can watch something intently. So I'm watching the floor intently, but we can also have see. That's a state. If you see something, you can't see something intently. So our brains are really good at working out the word, its meaning, which is that, and then which path to go in order to interpret the rest. So if you're on a train and you're going past a big field, you can spot something, which means you don't see it, now you see it. And so there's this change from not seeing it to seeing it. And in order for language to work correctly, you need to know that seeing is the main concept there. Because if somebody said, I spotted a deer in the forest, and you said, oh, did you see it? Well, yeah, I just said I spotted it. Spot means see. And so this type of thing gives us a lot of flexibility, and it makes systems that run really slowly, like today's AI, work really fast, because you're going from all of these different words into only a few meanings that then are very specifically defined. So what do we want to do with AI? We want to get progress. We want to solve these types of problems. And I believe that these 7 killer apps are going to radically change all of our lives. For example, automatic speech to text. My phone's up there recording, so I can't hold it. But if you've used Siri or the devices to generate text, you can speak to them. They type what you say. It always rhymes nicely. It usually rhymes nicely, but it's not necessarily accurate. I use the example of a street name. I'm going up Wallamata Road, and it likes to put Waller and then matter, M-A-T-T-E-R, rather than the Aboriginal word, because it's not trained in all the street names. Then it doesn't know, well, why should I choose the street name rather than these other words? Because it doesn't understand what the sentence means. But for example, we should be able to, in the future, walk into a room and have it all controlled by our voice. But in order for that to happen, we need a much better way of recognizing what's being said. Translation between languages. You can imagine going on a trip somewhere to France. You speak in English, it translates it to French. They speak in French, it translates it to English. If it works correctly, then that's a revolutionary way to work. Language learning with computer feedback. We're just kicking off a project with a colleague of ours who's a neuro-linguistic programming specialist. So I'm an NLP specialist, natural language programming. This guy's an NLP specialist, neuro-linguistic programming, or processing. And so he's a specialist in what is it that makes our brain work the way it does, so that you can take advantage of it and trick it into doing what you want. So this guy's been tricking people into learning languages for the last 15 years. And he does crazy things like, you put on some headphones and you listen to somebody speak in the target language. And your exercise is listen to this for 20 minutes. You go, well, I can't understand anything. But what he found was that just by listening to this, your brain is learning all of this stuff. And then when you go to repeat it again, they're picking up the sounds that are there. They're starting to be able to pick up where concepts are. And then by just tricking your brain, you can learn another language in 6 months. So this guy is focused on that. So we're working on the Speech Genie project. But you can see these other types of things, driverless cars. We were promised that in 2014 or something. But it's always a couple of years away. And digital agents. So if you're online, you want to buy something, wouldn't it be nice just to say, yeah, can you send me a couple of those, and have it interact with you or with your particular data to say, oh, hey, do you want me to send it to your house or your office, or that type of thing. And it comes back to this long-term problem. This was identified in the 1980s, but it still applies today. This guy Moravec pointed out that things that are easy for people are hard for machines, and things that are hard for machines are easy for humans. Did I just say that the same way, but backwards? Yeah. Anyway, you know what I mean? See, it's good that I'm speaking English. I don't have to convert it to logic. So because the machines today don't do what our brain does, we have to compensate by programming or doing different things. And I'll show you the killer app that we want, which is a dog of mine that proves the point. But here, this comes from the Brave browser. This is a large language model, and generated by machines.
Does everyone know what a large language model is? Is that a terminology or a term that you're familiar with?
ChatGPT.
Yes.
So this is a ChatGPT type system, and I asked it about the 1956 Dartmouth workshop where AI was named, and it comes through and it says that's where the name artificial intelligence was created. Participants, John McCarthy, Marvin Minsky, that was the guy that helped me, IBM guy, Claude Shannon from Bell Labs. So these are top people, and other notable attendees include Alan Turing, who previously. I thought, wow, that's amazing, because Alan Turing, the code breaker from World War II, the Enigma guy, yeah. In fact, possibly the guy that invented computers. But unfortunately, because he was English, everything he did was always classified, and now people think von Neumann's the guy that invented computers. But so this is all generated by machine. And if we look at Wikipedia now, you can see Alan Turing, died 1954, and there's this term machine learning. So machine learning was what they were studying there. But machine learning wasn't named until 1959, and Alan Turing died 2 years before the actual workshop. And so that's the type of, they call it hallucinations, but that's the type of limitation with the statistical techniques that are being used today. So one of my colleagues says, well, this is basically a system you can't trust. So unless you can be 100% accurate on the generation of your AI, you can't trust it. If you can't trust it, what can you use it for? And a lot of the work that's been taking place in recent years has been around taking the output from a system and then trying to work out where the errors are and then trying to patch them on the fly, which is about as big a problem as the whole problem of ChatGPT was supposed to solve in the first place. But don't take my word for it. I'm just a guy that focuses on brain science and application language. There's this guy, Tom Dietrich. So back in the 80s, he was a machine learning guru in the US. He's like the go-to guy of how do we, what evolved into the ChatGPT back in the 80s. And he did a tour 2 years ago where he pointed out that the current systems have flaws, and that it's this statistical knowledge base of the world. So but when I talked about you want to convert language into its meaning, that's like an opinion or something. I could say, Alan Turing's a great man, but somewhere on the internet you could find out Alan Turing was a moron. So how do you know which one to believe? And as people, we would go to the context and go, well, the genius one was written in the New York Times. This other one was written by this person I've never heard of, so I'll forget that and I'll go with the New York Times. But that's what we're doing when we're interpreting things. So there's statistical models of knowledge bases, and what we want to do is separate linguistic skill from world knowledge. And from what I've said so far, you must think that I've been colluding with this guy to simply write exactly what I wanted to be the solution that aligns with what I've been doing. But for me, that's the key, and I'll show you an example that highlights the fact that linguistic skill is incredibly powerful. That's how we learn language. That's how we learn everything. You don't go to school to learn language. You go to school to learn a topic, and you're learning the words, what they mean, and how they're used. So that's why we want to separate this, and it would mean that instead of spending $100 million to train ChatGPT, you could probably do it on a laptop like I've done, and then you could take the information that's relevant for an application and add that as particular knowledge. Okay, so let me just show you what I think is the key to the next generation of AI with a light example. So there's a dog chasing a ball. So the ball's bouncing behind it, and robots don't work quite like this. This one's worked out where the ball is, it's tracking it, it's going to jump off the ground. Sorry, bad camera work there, all 4 legs off the ground, and now there's a victory lap coming. So this is just an animal, and look, now it can do it with a nice jacket on. And we'll just give it an impossible task. It's got to do a 180-degree turn from a standing start, track the ball. Notice the hill's not level, so it's got to deal with that. Jumps, catches it, all 4 legs off the ground, and now it's back into the victory lap. So if we could do this with robots, you can imagine what we can do with different technologies that simply require motion, like driverless cars. That thing can see and it can navigate. So here we go. This is a $190 million startup in Oregon, I think. You can see here it doesn't have the same sort of, that's what it's seeing. The view isn't human level. I think I can recognize everyone in this room. And here's the Tesla robot. It's got sensors in its fingers, but notice when it puts the egg down, it kind of drops it. If you're putting an egg in an egg cup, you can feel it go into the cup, and you can do it gently so that you don't break it, you don't drop it. And this is the one not to do at home. This is how a robot can get up.
Somersaults and Tai Chi and all sorts of stuff.
Right. Okay, so that's the Boston Dynamics one.
Yeah.
So there's automation and all sorts of stuff. So where are we today with AI? People are predicting that 2025 there will be AGI, Artificial General Intelligence. And that's been defined for a long time. AGI is the solution to human-like capability. So it means that you should be doing what a human can do. So you need to be able to see and judge distance. This example. So they're predicting AGI in 2025. So you can imagine driving in the rain. There's a robot driving your car. It's raining, so you can't see very clearly. There's the wipers going across, and it's got to see what's happening on the road. And as it comes around the corner, if it sees something in the road, in about a quarter of a second, maybe half a second, you have to recognize what that thing is in the road, and then you have to make a decision. Do I drive into it? Do I drive into a truck that's parked? Do I drive off a cliff? What do you do? And that's the time frame that humans do it. So if we want to have AI at human level in 2025, that's a problem that needs to be solved, and people aren't working on that problem yet. Because they're trying to redefine AGI to be something that's solvable, not the actual problem that has been hanging around for 70 years. When we see somebody, we can recognize a human face in about half a second, and there's this 100-step rule that people always find very annoying. So we've got these slow neurons in our head, and neuron fires in about, I don't know, 0.05 of a second or something. Anyway, it's slow. But if you look at reaction time to get to half a second to recognize a face, you can only have 100 sequential neurons firing in order to recognize it. And the question is, well, you can't write a program with a loop to say, let's look at 10 million pictures and just keep looping around like you can do with today's AI. You've got to work it out in 100 steps. And the question is, how could you do that? The answer is cognitive science. We just emulate the brain. I'll get to how that actually works in a moment. And my book's a good place to start if you're interested in the theory. And what the book's covering isn't all the technical mumbo jumbo I'm going through now. It was just, how did I go from solving this 100-step rule into what's the right architecture to model on a brain? The other thing I've got in the last few chapters, so chapter 18 I cover the 7 killer apps that I showed earlier. And then the last 2 chapters I said, well, if we wanted to revolutionize language in 5 years, how would we go about that? And what we would do is we would build a languages company, and this is the one that's doing the particular languages, so English and Mandarin and Spanish and so forth, that lives down here. And up here we would do an industry. One of the industries over here would be the language learning application, because the application itself to teach English is, listen to this sound and then do this. But if it was French, it would be listen to this sound and do this. So provided we have this working and at the same time this working, we then can simplify how those languages work, and then we can do those killer apps that I was talking about in a very quick time. Okay, so we'll get into artificial intelligence, but first let me just take you on a quick tour of a working system. Sorry. Okay, so here's a couple of examples I prepared earlier. This is just coming from our developer experience interface that corporations can use. So there's a whole bunch of things. These are like the sequences of words that we would use in an example, different types of grammar, so again sequences, and then errors. So if you say to ChatGPT, can you draw me a picture of a gorilla, no, a monkey, and then we continue off, does it actually pick up the difference between gorilla and monkey? Is that a correction, or does it just give you the gorilla because it saw the gorilla, and that's a probable answer? Sorry. Okay, so we click on one of those, like error correction. If I have a conversation here, you can see on the left-hand side, call Beth, no Samantha, no John, no text. What does that mean? Well, I think it means text John. And then we say who is called, who is texted. So we've entered something and it's responded. And then we say who is called.
I don't know.
So statistically, call Beth was there, so why doesn't it say that? Because it's not what it means. And then if we ask the next one,
John.
so who was texted? John. And was this just a black box that's given us an answer? So today's AI is a black box. It's been trained. It gives you an answer. Why did it give you an answer? I don't know. It's what answer I got. And that black box thing is very annoying, particularly in certain industries like legal, where it gives you an answer and you go, is that right? I don't know, but that's the answer. So here, if I click on current context, in that conversation, you can see that the meaning of that first bit is text John. So there's some activity, who's being texted, well, John is. And if we wanted more detail, I'll set the room up almost perfectly, except for that little buzz. So here, you can see the we've got the representation. It's you who's the effector that is doing the texting, and John is the thing, which is the thing being texted. So again, it's all back to science, but we can do this stuff and improve on AI today. Well,
Is
I go
it
now.
the same principle as, like you said before, where you listen to something continuously? If the system listens to something continuously, it would eventually learn by default?
So how this one works is we build it like a normal compiler. We simply specify things and it gives us the answers based on a few rules. So for example, if we look at this one here, this one came from PubMed. So in PSS, IL-33 is released in the extracellular space from damaged salivary cells upon pro-inflammatory stimuli and or dysfunction of epithelial barrier. So I think it's a cancer drug, interleukin-33, or it's something that's used in treatment. And so what we're getting here is there's a topic. So in PSS, it's like saying in the New York Times. So there's our topic, and then in that there's something released. The thing that's causing it is this pro-inflammatory stimuli or the dysfunction, and the thing that's damaging is that's patient. Have to look up here. Interleukin-33 becomes in the extracellular space, and the extracellular space is the place where so we can decompose this stuff to a point where you could use it in medicine, which would be kind of cool, and you can rely on it because it's all testable.
In the previous example, what about the role of intonation?
Intonation?
Yes,
So
text.
yeah, in text we're losing a lot of useful information, and the way you get that back would be to annotate the text somehow, like say this was where the emphasis was in that sentence. In English, for example, you can have like 6 words, and if you put emphasis on different words in that sentence, it has a different meaning. And that's part of the context interpretation that's been quite well researched. So that's the meaning engine. I'm just showing that it's pretty thorough in what it can do. And if I go to conversation here, and I'll show you something I prepared earlier. So here, this is an exchange. I'll just run them and try and talk as it's going. So
The
I'm
man
not
bought a
standing
car
there.
from the dealer for $1.
So here, there's the idea of buying. That's the fact we're putting into the system. Can you see that at all?
Yeah.
So, oh, okay. I was trying to avoid
Who
getting
sold the
close.
car?
So when you say who sold the car, as a person, you go, oh, okay, so if he bought it and then this person's selling it, well, who's the one that sells? And what the system's saying is, well, because the meaning of buy is this and sell is that, you can then do the comparison and come up with the correct answer.
Who received the
And
car?
so this demo is just showing that if you receive something that's like buying, so it's giving you the man.
Who did the man pay for
Who
the
did
car?
you pay? Who did the man pay for the car?
Who was the car sold
Who was
by?
the car sold by? The dealer. So all of these things, which does your head in if you're doing this too quick. The point is it's all doable, and it comes back to the analysis of what does it mean, and there's a whole bunch of things that you can assume that buying a car means. So we've got there, the man doesn't have the car and then he does, and then the dealer does have the car and then he doesn't. So all of that type of stuff can then answer lots and lots of questions.
What does INGO mean?
ING, it's ingressive, so that's from the science. So it means an instantaneous change of state from something. But good question. And yeah, it's difficult to cover all of this in only a short period of time. I think I've got 15 minutes, so we can.
Some of that time for questions?
For questions, yes. So that's the system in action, and here. I know it's there. This is what's driving that system, which is basically a
Michael,
bunch
there
of.
was a question at the back.
Oh, how is Australia handling the AI situation? I know how Europe's doing, America's doing, but how is Australia handling it?
Australia is following the American lead at this stage. So Google and Facebook are encouraging Australian companies to adopt their technology. I think
most companies are using it, but I mean like governmental and militarily.
I believe it's being driven by the US. I'm not a specialist in that area, but
And also, it uses a lot of
phenomenon
electricity.
is that this technology, there's a couple of things going on. You've got the big companies that are developing it and looking to get people to pay for it, and that's being strongly supported by the CEOs of the big tech giants, so Microsoft and Google and so forth. There's the people that are machine learning or AI specialists, researchers. They're saying that this current technology is not working and it's not leading to the path that people want it to lead to. So you've got a disagreement between the experts in the field and the people promoting it as the solution to everything. And there's another group of people that are simply looking to use their expertise to move the science ahead. And they're proposing different ideas. They're, I think, called, the naysayers or the skeptics.
Also, I heard that it uses a lot of electricity, these
Right.
computers. Is that correct?
So the system I'm showing you runs on a laptop.
No, I mean
And-
AI
and is
in companies
built-
using AI in the computers use a lot of electricity.
Yes, yeah. So the US is proposing to support industry to build $500 billion of new data centers and power plants to drive those data centers to use their AI.
Yeah,
And-
well, a lot of them are already doing it with small reactors, aren't they? A lot of them are already building small reactors
Also, there's the nuclear power
Yeah,
plants that are being
nuclear
restarted
plants,
in order
yeah.
to help take some of the
because
load.
it swallows so much electricity.
Yeah, yeah. And for me, the green solution is to use cognitive science, because our brain runs on 12 to 20 watts of power, and we do more than any of these machines do. And
I've never heard that
now
before.
it's probably a little bit early to start building new power plants all around the world to do something when that thing probably won't be around in 10 years' time, because it's too expensive.
I heard that the guy who found it, I can't remember his name, said that he didn't actually find it. He said that it was there, that the AI was there,
Right.
and they just found a way to connect to it with science. You understand what I'm saying?
Like a Sam Altman or from OpenAI, or
Yeah, something like that. But he said that they said, how did you discover it? He said, I didn't. It was always there. We just found a way to connect to it through science and through algorithms and whatever. So, and then I heard that the guy in Google, the engineer who found that when he was chatting, that he discovered that it was sentient.
Oh, yes, right.
That was a big deal as well.
Yeah. So there's a lot of funny shenanigans going on in the world, particularly around the hype. So how ChatGPT works? It's a system that's been tested and improved for the last 10 years at least. And what it does when you put in some text is it compares to all of the text that it's had before, effectively, which is a extremely numerically intensive activity, computational activity.
Was it very quick though? Very quick.
Yeah, that's right.
Like in a second.
When these models are trained, the reason we need new power stations to make them run is it basically, if we started the universe and every second we did one computation to learn that, it would still have another 100,000 years to go to get to the end. So what engineers have done, like NVIDIA, at NVIDIA, they built a chip that takes a piece of the problem and puts it onto its own processor. And then they put lots and lots of processors and lots of memory, which are called GPUs, or graphic processing units. And then they package that up in such a way that you can do lots and lots of these computations in parallel. And so it's a solution to an engineering problem, and it works. It's just it's extremely expensive to run. And not only do you have power, you've got this incredible heat generation that's being caused, and so there's water cooling environments that are pulling this water through to take the heat away from the machines, and then you've now got heated water problems which contaminate the environment because you don't want hot water just pouring out. So lots and lots of environmental
Does
issues.
ChatGPT take its thing from Google? Because Google also does the same thing.
Right.
When you write in, it gives you all that information. But
Yeah,
not
Google's
us.
probably the source of today's.
Source, yeah.
They did a paper on a thing called Transformers in 2018, which said to translate text better, use this computationally intensive model. It's called a transformer. Google then built a thing called BERT, which is T stands for transformer and BERT, and it was supposed to
We
then
didn't ask, but
BERT. Yeah, they've the large language model implementation of this has been extremely popular since 2022 when OpenAI released their product to the public, and the public goes, wow, this is good, and it's free.
I see the school kids is copying now. They don't do their homework. They go home and they just put it in, and they get the. We know that it's through because it's too perfect. Most of them, you know which kids
Right.
are good and which are not. And suddenly they come up with this perfect language. Yeah, that's not right.
Yeah, and some of my colleagues around the world are very unhappy about that approach because it's like using a calculator to do an addition test. You're not testing what should be getting tested, I suppose.
Yeah.
Mhm.
So your theory is based on those 5 categories on the left-hand side?
These ones?
Yes.
So those are like the different
Yes,
applications.
This is the framework of your theory.
Yeah, so I can show meaning being broken down with this one, I can show the use of meaning in conversation, and then these are some samples that people can experiment with. And yeah, so it's a good view of the distinction.
So when it comes to the sense status, is lexical category
Right.
one aspect of the sense status?
Yes, so lexical category is the syntactic model of,
Yeah.
is it a noun, verb,
So
adjective,
you look at
adverb?
different categories in the sense status.
Yes. Yeah. So when you look at a dictionary out there, the English dictionary, you get a word and then you get its part of speech, which is a lexical category. It's unfortunate that linguistics has so many words that aren't the words that you get taught, that it becomes very difficult to have a conversation with somebody that's not an expert. So as I said, discourse pragmatics is something that Dan Valen uses as in his opening slide, and it took me like 8 years to work out what it meant. That's my fault more than
Do they
anything.
use abbreviations as well, like they do online, like when you're writing to somebody, you write see you later or whatever, and you write it in just letters rather as opposed to writing all the sentences.
Yeah, well, when you think of language, there's a movie I saw the other day with Bob Dylan, and the title of the movie was
The Unknown.
Complete unknown.
The Complete Unknown. Thank you.
Great song.
And I saw the movie title, and I thought, I know that song.
Yeah.
Complete Unknown. So in my head, I can connect those string of words directly to the song, and then you've got the rest of it that's in your head and the melody. You can do the same thing with brute force, and you can just push it through this neural network for $10 or something, and it gives you the same answer. But then you've got to choose amongst the different complete unknown. It could be literal. The title could be about something unknown.
Yes, Jeff, we're going to read even a moment.
Sure.
This looks like it's going to be, or could be, quite a disruptor with the current trajectory of AI. How do you see that playing out, and what sort of application is there out there of this at the moment?
Well, so we're pretty active in social media. There's not a lot of attention being given at the moment because if you've got Google and all the tech giants all pushing one technology, there's a lot of media that then follows that, and it's pretty hard to get seen above the noise. Typically we're hearing AI is just exponentially improving, but they're exponentially improving against the industry benchmarks that the industry just determine. And if you look at what happens in a week, it can be pretty horrendous to read through 50 new papers that describe some very technical implementation. And so I just fight back by saying, well, let's compare it against the goal. Where's the driverless cars? Not this year, next year, 2 years, 4 years, 10 years. So we're seeing that the windows to solve the real problem are still 10 years out. And it's just the really cool CEOs that are saying this year we're going to see a breakthrough in something that they can't do, and they're not working on it. And so I just try to educate people with where we're at, and we're talking to a lot of people in that space. But I don't think we can break through quickly, because we probably need to do a deal with somebody like a Google that just has an interest in solving the problem, and we just have to get through the noise of, do you have something that's really different? And that was one of the reasons for writing the book last year, because I guess it's like 3 months to write, a couple of months to edit, and then get it out there. So we're still kind of early days.
Our approach is, as John mentioned, those 7 killer apps, is to start with the language learning, and next week we go to meet the language educator that John mentioned in Malaysia to work with him, and we'll be raising capital to produce the first language learning app with natural language understanding that John's just discussed.
Excuse me, what's your role?
So I'm co-founder with John in our company,
Okay.
and also his wife.
Okay.
We met in IBM. I won't tell you what decade or what millennium that was.
That's okay, I think you were the same, you both were at the same age as me.
So I thought I should be plugging my book while we're talking. Yeah.
Can I just ask, do you think this has pushed the emphasis? You have no chance of succeeding in this field unless you have a really strong understanding of what we used to call grammar and syntax.
Right.
So it's pushing the emphasis back away from that. Well, not necessarily away from it, but you're not going to succeed here unless you have a strong grounding in how all languages work, or grammar, or
Yes.
syntax, semantics. So that's something fairly new, isn't it? Whereas computing 2 decades ago was maths, programming.
Right.
Is that a fair assumption?
Yeah, so the unfortunate thing was when ChatGPT went viral in 2022, one of the things I was predicting was that you can never get multiple languages to work well on one platform. And unfortunately for me, these things do about as good a job between languages as they do in a single language. So when I did my demonstration test in 2022, unfortunately it gave me a really good answer. And I then had to revise, okay, well it can do this, but it can't do that. This model I could show to any world expert in linguistics or in computer science, and there's enough now to push the case with anyone. In 2016, when we first set up a US company to promote this, we basically got hammered in all of the due diligence meetings, because we would say, here's what it does, it works. I go, great, okay, here's your due diligence guy, he's an expert in deep learning, and he would say, how does it work? And we explain it, and they go, well, I think you can do this with deep learning. It doesn't do it yet, but it'll do it soon. And it's very hard to argue against the it's coming soon type argument. And in due diligence, if you're pitching to a company and they're getting an expert, and their expert believes that the current system's good enough, you can't win. So
It's getting rid of quite a few jobs.
yeah, and probably not to the degree that people are predicting. So back in 2022, Goldman Sachs said expect 300,000 jobs. I think that was the number. Expect 300,000 jobs to disappear very shortly. And they then revised it about a year and a half later and said, no, we're wrong with that. Because it's not really a technology that can replace humans. It can augment humans, but the errors have to be weeded out by somebody that's more trustworthy.
And it very much depends on the use cases. Where ChatGPTs and the large language models excel is generating text. As John's probably demonstrated, it's not always accurate, but it's a good bluff, and it makes you think, hey, wow, there's a human behind there somewhere. When you look at the industries like legal or financial or medical, where there's just no allowance for mistakes. Those use cases with like chatbots require that a non-black box. You need a human-like understanding, and that's what this cognitive science provides. So this is back to a question that we had just a few minutes ago. That is our differentiator, and yes, it's hard because we're up against very deep pockets, but ours is faster, cheaper, accurate. It doesn't hallucinate. And so for those regulated industries and enterprises that care about their brand, they can't use this. It won't, the chat GPTs or that architecture.
Yeah, the term hallucinate comes from the anthropomorphizing an error. So if a person makes a mistake because we think it's right, that's we hallucinated the source. In the case of these systems, they actually generate errors, which is confabulate in human terms, or they're just generating an error because they don't have a knowledge base to validate it with. That would be a much more complex system. Yeah, and people are saying now that maybe we'll get much faster quantum computers to do this, and what it will do is it'll generate much faster errors. But the fundamentals behind it just don't stack up. I was going to say Terry Winograd. He's at Stanford. He's one of the top guys that was involved in language understanding back in the 70s. And I had a good meeting with him in 2016, and he gave me great advice. He said, "Look, I know what you're saying. You say it terribly, and what you have to do to convince others is go and learn the science, go and explain it in scientific terms." And I've spent the last 10 years, 9 years to be able to do that. So now I can point to 50 papers that justify what we're doing.
And that's probably your alarm to say...
It's time for people to have some cookies and tea or to get moving.
And Arnott's biscuits. If you'd like to buy a book, we've got some paperbacks and John will inscribe them. So please stick around if you'd like to talk to him and or purchase a book.
And you can buy them online on Amazon, so that's the details there. There's a few handouts if you just wanted to grab one of those.
And if you want to follow John and his work, he's on LinkedIn, he's on Twitter, or you can email him at john@pat.ai, and he'd love to take more conversation or call questions about his work. So thank you very much for your engagement.